In the last video, we began considering the problem of 7 brothers each putting on a different hat. And we found out that there was in total 5,040 ways for the 7 brothers to put on a hat. But that if we required that each of the brother put on a hat that was not their own, there were only 4 possible cycle structures. The first cycle structure listed here is the 7 cycle. Here, I'll just give you an example. A, B, C, D, E, F, and G. And we want to count how many different 7 cycles there are. So we have to put 7 letters here. Any of the 7 letters can go in the first spot. Then, of the remaining 1 letter is used up, any of 6 letters can go in the second spot. Any of 5 can go in the third. Any of 4 times 3 times 2 times 1. But we're not yet finished. We have to remember that thing that we noticed in the last video, and I'll show it right here. Consider this 7 cycle to this one here, which when you first look at it, looks different. In this second cycle, B puts on C's hat, C puts on D's hat, D puts on E's, E's F, F G, G A, and A B. That's exactly the pattern on top. B puts on C, C D, D E, E F, F G, G A, A B. And so these are 2 permutations that are the same but look different. The rule is you can have any of the 7 letters as the first letter, and if you follow the progression that we have here, it's the same permutation. And so what we have to do is divide our number here by 7, because there's 7 permutations that look different that are the same, and when you work that out, that's going to be 720 ways. Okay, please pause the video and please try doing the 5 cycle plus the 2 cycle. Okay, in the 5 cycle plus the 2 cycle, we have A followed by B, C, D, E, and then F and G. So we have any of 7 different ways for the first letter, times 6 for the second letter, times 5 for the third, times 4, times 3. But any of the first of the cycle letters can go at the beginning. We've overcounted. We have to divide by 5. And then there's the question is, do we have to change the number because of F and G? And the answer is no. Once we've picked the 5 in the 5 cycle, the remaining 2 letters, they just must interchange hats. So it's just times 1. And if you do that math, that's 504 ways. So try now the 4 cycle and the 3 cycle, and we'll compare answers. So please pause the video and try the 5 cycle and the 4 cycle. 4 cycle and the 3 cycle. Okay, so I'll do that. A, B, C, D, E, F, G, and A can be any of 7 times 6 times 5 times 4. We've overcounted. We have to divide by 4, any first letter. And then we have another cycle, any of 3 for the first letter, any of 2 for the second times 1, and we have to divide by 3. And so if you do that math, you come up with 420 ways. In the last case, the 3 cycle, the 2 cycle, the 2 cycle needs to be considered a little more carefully. Please pause the video and see what you come up with there. Good, so one more case. We have a 3 cycle, And how many different ways? We could have any of 7 here, times 6 times 5, divided by 3. And now we have the question of the remaining 4 letters. They have to go into 2 pairs of 2. So D could pair with F, D could pair with G, or D could pair with E. Once D's paired, the other guys have to be one way. There are only 3 ways to do the 2 cycles. So it's times 3. And that's 210 ways. If you sum up all the number of ways, that adds up to 1854 ways. And I just would like to say one really cool thing, I think, mathematically, which is that 1854 divided by 5,040 is equal to 0.3678. So that's the answer to the question. But the cool thing is to take the inverse. 0.3678 to the minus 1 is 2.718. And you may recognize that number from calculus. This is e to 4 sig figs. And actually, it turns out, as the number of brothers increases, the probability that none will wear their own hat goes to 1 over e. And so this is a problem where the irrational number e improbability just naturally appears. And we'll do more examples like this in class.